Chemical Kinetics Part 16, Reaction Mechanism. Reaction mechanism tells us the steps by which a reaction occurs. And reaction mechanisms can get as detailed as to tell us the order in which the bonds are broken in reactants and the order in which the bonds are formed in the products. We don't necessarily have to get that detailed, though. Now, elementary reactions are reactions that occur in a single step or single event. So, for example, upon collision of two molecules with proper orientation and sufficient energy, a reaction occurs, and then products are formed and the reaction's over. But some reactions do proceed in multiple steps. Here's a vocabulary term we should be aware of. It's molecularity. Molecularity describes the number of molecules that act as reactants in an elementary reaction. So for molecularity of an elementary reaction, if there's one molecule involved, we would say it's unimolecular. If there are two molecules involved in an elementary reaction, we would say it's bimolecular. And if there are three molecules involved, and that would be rare because that means that we'd have to have three molecules all colliding in the same place at the same time with the proper orientation and sufficient energy for a reaction to occur. Now it's rare, but it does happen sometimes. Then that elementary reaction would be termolecular. And there's really just such a remote chance of more than three molecules colliding in the same place at the same time with proper orientation and sufficient energy that we won't see elementary reactions that are really beyond termolecular. So it's important to understand that when we're dealing with multiple step reactions or multi-step reactions, there will be at least one intermediate that's involved. And we could say that for multi-step reactions, the sum of the equations of all the elementary reactions, or all the steps, equals the equation of the overall reaction. Let's take a look at an example here. We have NO2 plus NO2 forming NO3 plus NO in our first step. This is our first elementary reaction. And then NO3 plus CO forms NO2 plus CO2 in the second step, or the second elementary reaction. Now if we add up all of the reactants and we add up all of the products and then we simplify, and we can see that we can cancel out an NO2 on the right and on the left, and we can cancel out an NO3 on the right and on the left. So then we get NO2 plus CO forms NO plus CO2 for the overall reaction. Now we could say that we have an intermediate here. An intermediate is a molecule that is formed in one step and consumed in another step. So our example of an intermediate is NO3. Check out how NO3 gets formed in this step and then gets consumed in this step. Now you might say, well, what about NO2? That's crossed out as well. Well, we simplified that from the final overall reaction equation, but we can't say that NO2 is an intermediate, because notice that NO2 is a reactant. So an intermediate is a chemical that's not a reactant or a product. Again, it's a chemical that gets formed and then reacts away from one step to another. Let's take a look at a reaction profile or an energy profile, or you could call this a potential energy diagram as well, for that reaction. This is the same reaction we were just looking at. And we can say that this first step happens in this first peak on the graph. And then the second step happens in this second peak on the graph. So overall, we start with these two chemicals as reactants, overall, and we end up with products of these two chemicals. Oops, I have a little mistake there. That should just be NO plus CO2. All right, so the intermediate NO3 will be formed between those two reactions. It's formed at the end of the first reaction and then reacts away as the second reaction progresses. Notice that the CO was there from the very beginning, but it didn't take part in that first reaction. It was one of the reactants. So it was really doing nothing in this progress of the overall reaction. That first step doesn't involve the CO, but it was in the container. All right, so transition states are always the peaks of the graphs, and the transition states are the points where some of the bonds of the reactants are being broken. So the transition state here, we're going to see the NO2 bonds being broken. And that would be forming the NO3 and forming the NO. Now in this second peak, the NO doesn't really do anything. It's not part of the second step. So that's just going to remain as a product. And what we're going to see is in this transition state, the NO3 bonds are going to be broken, and the CO bonds will be broken. And then as we begin to form the final products here, we're going to be forming CO2. Notice that the NO was already formed after that first peak on the graph. So transition states aren't molecules. They're the transition state or the activated complex where we've broken the bonds of the reactants. Now let's remember that differential rate laws are determined by experiment using the method of initial rates. And these are differential rate laws when we have a single reactant, A, for a zero order, first order, and second order reaction. Now these rate laws can also be predicted if we have a correct reaction mechanism. We would say that a proposed reaction mechanism is valid when it predicts a rate law that agrees with the experimentally determined rate law. So we can use the method of initial rates to determine the rate law with experiment or by experiment. And then we can propose some different steps of a reaction or some different elementary reactions that when they all come together would give us a rate law that's predicted based on whatever we've proposed for those elementary reactions. And that's what we're going to do here today. An important point here is that rate laws for elementary reactions are based on their molecularity. So here's some examples with different elementary reactions of what the rate laws would be for those elementary reactions based on the molecularity. So notice we have a unimolecular reaction here. In other words, we have a single molecule or a single particle as a reactant. So then the rate law would be that the rate is equal to the rate constant K times the concentration of that reactant. If we have a bimolecular example, say two of the same reactant forming products, this is what the rate law would look like. Here's another bimolecular example where we have two different reactants. Now remember that termolecular reactions are rare, and anything greater than termolecular elementary reactions are of such remote possibility that we won't have to consider those. So if you have three of the same molecules reacting as reactants, forming products, we'd have that as our rate law. Or if you have two of one molecule and one of another molecule, we could see a termolecular rate law like that. And if you have three different molecules, we could see a termolecular rate law like that. But once again, rate laws for elementary reactions are based directly on whatever the molecularity is. So what about rate laws for multi-step reactions? Well, we can say that each step or each elementary reaction has its own rate law and rate constant. And that the slowest step is the rate determining step or the rate limiting step. And often in reactions, we'll find that one step is much slower than the others. It makes sense that if there are several processes that are occurring, the slowest process would determine how fast the overall process would occur. Now here's our main point now. The rate law for a multi-step reaction is always equal to the rate law for the slowest elementary reaction. It's equal to the rate law for the slowest step. All right, so let's say we have a mechanism with a slow initial step. Here's an example. The proposed reaction mechanism is that NO2 plus NO2 forms NO3 plus NO. And then NO3, being an intermediate, combines with CO and reacts away and forms NO2 and CO2. So we have an NO, and one of these NO2s, one of these NO2s cancels out. So an NO2 and a CO carry into the overall reaction as reactants. The intermediate would react away. And then we have NO and CO2 as our final products. Now we said that step 1 is the slow step, the rate determining step. What that means is that the rate of the step 1 reaction is slower than the rate of the step 2 reaction. It's a smaller rate. Well, that means that the rate constant in the rate law for the first reaction, the step 1 reaction, is smaller than the rate constant in the second step reaction. Now take note, the intermediate NO2 is being slowly produced in the first step and quickly consumed in the second step. All right, so let's consider that reaction again. Remember that the rate law for elementary reactions is just based on the molecularity. So we can say that for this first step, the rate law is that the rate is equal to, we'll say, K1, because we're talking about the first reaction there, multiplied by, well, we have two NO2s there, so it'd be NO2 squared. The rate law for a bimolecular reaction where both reactants are the same would look like that. And the rate law for the second step would be rate of the second reaction, or rate subscript 2, is equal to our second rate constant, K subscript 2, times the concentration of NO3 times concentration of CO. Now this is the slow reaction, and this is the fast reaction. And both of these rate laws are determined directly from the molecularity of the elementary reactions. Now here's the overall reaction, and let's say that we have determined by experiment that this overall reaction is second order with respect to NO2 and zero order with respect to CO. So second order in this chemical for this overall reaction, zero order in this chemical. Well, if it's zero order, anything to the 0 powers 1, we can neglect that and just express it as K times the concentration of NO2 to the second power, second order with respect to NO2. And we would determine that by experiment, right? We might use the method of initial rates to determine that. Now notice that because the overall experimentally determined rate law, this right here, is the same as the rate from the first, the rate law from the first step of the mechanism, the rate determining step, that the proposed reaction mechanism is a valid reaction mechanism. If that wasn't the case, if the overall rate law didn't equal the rate law for the first step, then we couldn't say that this is the reaction mechanism with the first step as the slow step or the rate determining step. Now, just because this is a valid mechanism doesn't give us conclusive proof that it is in fact the mechanism. There might be some other proposed mechanisms that would also have the overall rate law match the rate determining step. But we could say that this is one valid mechanism. So that was a mechanism for a reaction with a slow initial step. What if we have a fast initial step? Well, this is going to be a little bit more complex. Since the rate determining step, the slow step, is not the initial step, the overall rate seems to have an intermediate. Remember that anytime we have a multi-step reaction, there's an intermediate. And that's going to be a problem for us because we don't want to have our rate law expressed in terms of an intermediate. Let's take a look at an example. Let's say we have this proposed mechanism where we say that NO plus Br2 forms NOBr2 in our first step. That's our fast step. That's our first elementary reaction. And then in our second step, NOBr2, that's our intermediate, combines with NO to form two NOBRs. Our overall reaction is that two NOs, there's two NOs, and one Br forms two NOBRs. Remember, if you combine the reactants of the elementary steps and the products of the elementary steps, simplify that down, you get the overall reaction. Now, the elementary reaction, because its rate law can be determined by its molecularity, would have this for the rate law. So the rate of the first elementary reaction, step 1, is K1 times the concentration of NO times concentration of Br2. And the rate law for the second step, again, can be determined by its molecularity because it's elementary, is that the rate of the second step is equal to K2 times NOBr2 times NO. Now, if this is the slow step, if this is the rate determining step, we have a problem. We can't really say that the rate of the overall reaction is equal to the rate of this slow step because it would contain an intermediate. And the intermediate is not present in the overall reaction equation. So what are we going to do there? Well, let's take a look at what we can do. This is for reaction mechanisms with a fast initial step. Same reaction that we were just looking at. Now we could determine by experiment what the rate law is, and let's say we've determined it to be this using the method of initial rates. So the reaction is second order with respect to NO and first order with respect to Br2. Now there's one possibility, and that is that because we have two NOs and one Br, that this is in fact a elementary reaction, and because it's an elementary reaction, we could say that the rate expression or the rate law would be based on its molecularity. So since there's two of these molecules, it'd be second order with respect to that chemical, and since there's one of those molecules, it's first order with respect to that molecule. The thing is, termolecular reactions are pretty rare. Let's see if we can come up with a mechanism so that we can, let's say we can use this mechanism and show that this mechanism actually works. Now, to do that, we have to make some assumptions. Let's assume that the intermediate, NOBr2, right here, is in equilibrium in the fast step. And that's a technique that we're always going to use when we have a fast initial step. Or in other words, when the rate determining step, the slow step, is not the first step. We're going to assume that the fast step has an equilibrium going on. And also we're going to make the assumption that the intermediate doesn't accumulate in any big numbers, that the intermediate is either reacting backwards to form these chemicals, or some of it is slowly forming this chemical. So if you haven't studied equilibrium reactions, an equilibrium is where a reaction can go in the forward and reverse directions simultaneously. So there would be a rate for the forward reaction and a rate for the reverse reaction. And one of the properties of equilibrium reactions is that the rate of the forward reaction would be equal to the rate of the reverse reaction. So since this is step 1, we'll call it rate 1 and rate -1, where -1 would be the reaction going back that way. So we can plug in because this is an elementary reaction, we can plug in for the rate laws using the molecularity. In the forward reaction, the rate law would look like this, where we have K1 as the rate constant. And for the reverse reaction, using this as a reactant and forming these as products, this is what the rate law would look like. And we can say that the rate of the forward reaction equals the rate of the reverse reaction, so these two are equal. Now you can rearrange this equality and solve for the concentration of the intermediate, NOBr2. So we have to get rid of this rate constant, or K-1, and it goes down to the bottom over there. Then what we're going to do is we're going to say, well, if this is the slow step, the rate determining step, then the overall rate of reaction that we determined by experiment should be equal to this rate of this slow step, this rate determining step. So let's write down the rate determining step for that, or let's write down the rate law for that rate determining step for step 2. We'd say that rate 2 is equal to K2 multiplied by that reactant's concentration and that reactant's concentration. We can see that's bimolecular there, right? There's one of each of those, so 2 different molecules. And then for the concentration of NOBr2, we're going to substitute in this expression over here. And when we do that, we get that the K2 multiplies by, substituting in for that, we take all of this and plug it in between these parentheses, multiplied by that. Now, that's a constant times a constant divided by a constant. We can combine all 3 constants into one constant. We'll call it K. And then we have NO concentration, Br2 concentration, and NO concentration again. Well, anything times itself is that thing squared, so it's NO concentration squared times the concentration of Br2. Well, guess what? This is the rate law for the second step, the rate determining step, where we've substituted it in for the intermediate. And it matches the rate law determined by experiment, using the method of initial rates, for example. So just take note here that given this reaction, this overall reaction, and given this experimentally determined rate law, it's more likely that the previously proposed mechanism that we just went through for step 1 and step 2, where step 2 is the slow step, and that first step, that fast step, was in equilibrium, is correct. It's more likely that that's correct because the possibility of having a termolecular reaction is pretty rare. It's a pretty small possibility. So we can say that whenever the initial step is not the rate determining step, whenever the initial step is not the slow step, in other words, when the fast step precedes a slow step, assume that the fast step is in equilibrium. Remember that whenever you have an equilibrium reaction, the rate of the forward process equals the rate of the reverse process. And then we can plug in the rate law expressions for the forward and reverse processes and solve for the concentration of the intermediate. Then we substitute the intermediate concentration into the rate law for the rate determining slow step process. And if it's equal to the experimentally determined rate law for the overall reaction, then we have a valid mechanism. And then before we wrap it up, just one final note here. Reaction mechanisms can get very complex. For example, in biochemistry, biological processes can be very, very complex. And we would see that there could be intermediates that cannot sometimes be ignored, especially when you're doing biochemistry. So we'll also see reaction mechanisms that can get very long with a large number of steps, sometimes over 35 steps. So we're just kind of scratching the surface here of reaction mechanisms.